In this video, we're going to do example 5.6, the magnetic dipole. They give us a small circular loop with radius b. Now, we have to emphasize that this is small because later we're going to make an approximation that relies on the size of the loop being small compared to the distance from which we're observing it. And that loop carries current I as usual. Now the steps that we're going to follow here are step 1, choose coordinates. Step 2, find A by integration. And involved in there is step 2A, make some approximations. And then step 3, find B from the curl of A. All right, so step 1. The coordinates are going to be spherical. The center of loop is at the origin. And the loop is in the xy plane. Let me draw you a picture of that real quick. Here is our Cartesian coordinate system. Good heavens, that wasn't great, but that's okay. Clean that up a little bit. There, now my y-axis looks okay. What I'm going to do on here is I'm going to draw my loop. My loop has radius b. And also in this coordinate system, I'm going to have, here are my definitions for the angle coordinates. So the spherical coordinate system has, at some point P, we have a distance big R, the angle theta, which is the angle from the z-axis, and then if we project point P onto the xy plane, the angle from the x-axis is phi. Hopefully that is reasonably clear. P is existing somewhere between the x and y axes, and it's not in the xy plane, it's someplace above it, and then we project it onto the xy axis to find out what phi is. Now, in this coordinate system, we have our definition, well, not our definition, but our integral equation for A, which is equal to, and we're going to say that this is A at that point P, at some point P anyway. A is going to be equal to mu naught I over 4 pi integral around the closed contour of dl prime over R1. R1 here, R1, this isn't really an equation here. R1 is the distance from P prime, a point on our current source, to P, our observation point. Now, from this picture, clearly the magnetic field can't depend on phi because of symmetry. If we were to rotate this whole thing around the z-axis, we would have the same picture. So it doesn't matter where we define phi to be. So this is phi in the unprimed coordinates. So that means that we can evaluate this integral at any particular location in phi, and then generalize to say that that's true at all locations in phi. All right? So evaluate integral at any phi, then generalize. So we're going to choose phi is equal to pi over 2, mostly because it's convenient. It makes all of our numbers fall out nicely later. We're going to find A at P equals R theta pi over 2. Here's an important thing. We're still going to vary phi prime from 0 to 2 pi. It's still going to depend on phi prime. So let's take a look at this integral. By choosing phi equals pi over 2, we're saying that P is in the YZ plane. Now, our differential little length vector of integration, dl prime, is equal to minus a hat x sine phi prime plus a hat y cosine phi prime. All that times b, because that's the radius in our circle, d phi prime, because that is our differential length, and this is its unit vector. All right. Now, here is an important thing. We're going to make a symmetry argument. I'm going to draw my coordinate system again. Try to get the y-axis right this time. It's a little better. Here's my circle. I said that we're choosing P as a point in the YZ plane. P. There we go. Now, if we have a differential current element here, IDL1, and we have another one here, IDL2, both of these contribute an x component and a y component that you can see at P. So I'm scrolling down a little bit so you can see the parts of DL. Now their x components have the same sign, so they add. Their y components have the opposite sign, so they cancel. This is because of the difference between sine and cosine of phi. So we can then rewrite our integral for the magnetic vector potential as minus a hat x mu naught I over 4 pi integral from 0 to 2 pi b sine phi prime over r1 d phi prime. What I've done here is I have dropped the y component of dl because we have made this symmetry argument that they're always going to cancel out, and we are only going to have the x component contributing to the integral. Now, we're later going to be we've already made the symmetry argument that whatever we find here is true everywhere, and we just have to generalize to all values of unprimed phi for all the observation points. What that means here is that we have to convert this x-directed unit vector into its equivalent for whatever the observation point happens to be. And what that means is that minus x-directed unit vector in the yz plane is actually equal to a sub phi. So that's going to be a sub phi there, and then we're going to have all the same stuff. Mu naught I over 4 pi, integral 0 to 2 pi, b sine phi prime over, that's an R1, not an R, R1, d phi prime. Cool. Now, here's the part when we make approximations. Start with the law of cosines. R1 is equal to, let's write R1 squared, is equal to R squared plus B squared plus 2B big R cosine psi, that's the angle between the vectors from the origin to P prime and the origin to P. So that's psi is angle between OP prime and OP. That cosine psi, I'm just going to write this out, but you can verify this by looking at the triangles. Cosine psi is equal to sine theta sine phi prime. This is the part where we make the approximations. 1 over R1 is equal to 1 over a whole bunch of stuff. Oh, I'm going to try and draw a flatter line there. 1 over big R times square root of 1 plus b squared over big R squared minus 2b over R sine theta sine phi prime. Oh, my law of cosines has an error in it. My law of cosines, this should be a minus. There, fixed it. All right, so approximation number 1. B squared over R squared is approximately 0 because B is much less than R. We're all okay with that. We're just going to get rid of it. Approximation number 2 is we're going to use the Taylor expansion for 1 over square root of 1 plus x. In which case, we started with 1 over r times square root of 1 minus 2b over r cosine, sine theta sine phi prime here. And we're going to say that that is approximately equal to 1 over r times, no longer underneath the fraction or in a square root, 1 plus b over r sine theta sine phi prime. Sorry, I ran out of space there a little bit. Now, finally, we're going to write down again our integral for the magnetic vector potential A is equal to a hat phi. Remember, because in the yz plane, minus a hat z is equal to a hat phi. And we're trying to say that this is going to be, whatever we find here is true for all phi, times mu naught I times b divided by 2 pi r integral from minus pi over 2 to pi over 2. Now what I've done here is I've decided to evaluate only half of the integral. So instead of going from minus pi to pi or from 0 to 2 pi, I'm doing minus pi over 2 to pi over 2. And then this factor of 2 here used to be a 4. So I'm actually gaining a factor of 2 and cutting the integral in half because of symmetry. The thing inside the integral is 1 plus b over r sine theta sine phi prime, and then we have sine phi prime d phi prime like we had before. All right, so the integral from minus pi over 2 to pi over 2 of 1 times sine phi prime is going to give us 0 because that's going to evaluate to minus cosine, and then integrating from minus pi over 2 to pi over 2 cancels out. So that part is going to give us 0, this part right here. The rest of it, we're going to use the fact that integral from, well, that the integral of sine squared phi prime d phi prime is equal to the integral of 1 plus cosine of 2 phi prime all over 2 d phi prime. And again, since these bounds are symmetric, the cosine term is going to cancel out, and we have the integral of 1/2 from minus pi over 2 to pi over 2. So integral sine squared phi prime d phi prime is equal to pi over 2. And that's because of our bounds, not because that's true in general. All right. So if I substitute in the result of that integral back into my expression for a, which was up here, so that goes in the second term, then what I get for a is just a hat phi mu naught I b over 2 pi r times b over r times pi over 2. So these pi's cancel out. The 2 and the 2 combine to become a 4. We got a b squared and an r squared. We get rid of all of that stuff. And never forget the sine theta. All right, so now in order to find B, we need to get the magnetic flux density, and that is equal to, as always, the curl of A. That we're going to use the spherical coordinates curl because that's what we need to do. So that's going to be equal to all those constants, mu naught I b squared over 4 times, this is a little bit hard to squeeze in this determinant, but I'm going to try, a hat r over r squared sine theta, a hat theta over r sine theta, a hat phi over r, partial partial r, partial partial theta, partial partial phi. Lastly, a sub r, r a sub theta, r sine theta, a sub phi. There. Now, all we have in our particular situation right now is a sub phi. We don't have any of the other terms. So this works out to be equal to mu naught I b squared over 4 times a hat r over r squared sine theta, partial partial theta, sine squared theta over r minus, can I fit this? Yeah. A hat theta over r sine theta partial r sine squared theta over r. All right, because sine squared theta over r is our the part of A that is not made of constants, so that's what we're dealing with right now. Evaluating those integrals, those derivatives, we have mu naught I b squared over 4 times a hat r over r squared sine theta. Those parts stay the same because the derivative doesn't operate on that part. The derivative with respect to theta of sine squared theta is equal to 2 sine theta cosine theta by the chain rule. And then we have over r, because r doesn't depend on theta. We're going to have a sign flip here, which is due to the derivative of 1 over r with respect to r. A hat theta over r sine theta times sine squared theta over r squared. Now, simplifying and adding all the important bits together, the parts that match, I mean, we end up with mu naught I b squared over 4 r cubed. Both terms end up with r cubed dependence. There's an r squared times an r and an r times an r squared there. And that is multiplied by 2 a hat r cosine theta plus a hat theta sine theta. Okay, so key things here. 1 over r, that magnetic flux density depends on 1 over r cubed. As you move away from it, the r component, a hat r term, has cosine theta dependence. And the theta term has sine theta dependence. Those are key things to notice about this. Also, the magnitude of, oh my goodness, it's just erasing everything I write here. It wants me to write further apart. Okay. The magnitude of the magnetic field is proportional to the area of the loop. So that's b squared. In fact, you could write this equation if you were going to write it again. Mu naught I times area divided by 4 pi r cubed times 2 a hat r cosine theta plus a hat theta sine theta. All I did there was substitute in pi b squared, which is the area of the loop, into that thing, and then I added another factor of pi on the bottom to cancel all that out. So those are some key things about the magnetic